Hi, so today in part 2 of special relativity, we're going to discuss time dilation, length contraction, the Lorentz transformation equations, Lorentz velocity transformation, relativistic mass and the relativistic form of Newton's second law, and the relationship between mass and energy, massless particles, and relativity and electromagnetism. So we will now discuss time dilation. So let's consider a vehicle moving to the right with a speed v, okay, as shown here. And suppose that there is a mirror at the ceiling of the vehicle and that there is an observer at O dash who is at rest in the system, okay? And this observer is holding a laser at a distance d from the mirror. So at a certain instant of time, a pulse of light is emitted from the laser directed towards the mirror, and then at some later time after reflecting from the mirror, the pulse of light arrives back to the laser, okay? So suppose that this observer at O dash carries a clock C dash to measure the time interval delta t dash, okay, delta t dash here, between the two events. So event 1 marks the instant the laser emits the pulse, and event 2 is when the pulse arrives back at the laser after reflection. And because the light pulse has a speed of c, the time it takes the pulse to travel from O dash to the mirror and back to O dash can be found from this relation. So it's the distance traveled over speed, so it's equal to 2d over c. So now consider another observer, O dash, in a second frame who observes the same pair of events. So according to this observer, both the mirror and the laser are moving to the right with a speed v. So by the time the light pulse from the laser reaches the mirror has already moved the distance of v delta t over 2, right, here. And delta t is the time it takes the light to travel from O dash to the mirror and back to O dash as measured by O. And so according to the second observer, if the light is to hit the mirror, and because of the motion of the vehicle, it must emit from the laser at an angle with respect to the vehicle direction, okay? And so the light in the second frame travels farther than in the first frame. And according to the second postulate of special relativity, both observers must measure c for the speed of light. And because the light travels farther in the second frame, the time interval delta t measured by the observer in the second frame is longer than the time interval measured by the observer in the first frame, okay? So this is because the speed of light is the same, which is equal to c for both observers. So using Pythagoras theorem, you can see that c delta t over 2 square is equal to v delta t over 2 square plus d square. And so delta t is equal to 2d over c square root of 1 minus v square over c square. And because delta t dash is equal to 2d over c, then delta t is equal to delta t dash times gamma. And this expression is equal to gamma here, okay? So this result shows that the time interval delta t measured by an observer moving with respect to the clock, and note here that the pulse round trip represents the clock, or 1 tick, okay? So the time interval delta t measured by an observer moving with respect to this clock is longer than the time interval delta t dash measured by an observer at rest with respect to this clock, okay? And this is because gamma is always greater than unity. And so delta t is greater than delta t dash, and this effect is known as the time dilation. And delta t dash is known as the proper time. So the proper time is the time measured with a single clock at rest in the frame in which the event takes place. So let's consider the situation according to observer O, A clock at rest relative to O will run faster than a clock in motion relative to O. Okay, so according to observer O, uh, the time between ticks of a moving clock is equal to gamma delta t dash, and it is longer than the time between ticks of an identical clock at rest relative to observer O. Okay? Um, and so it is often said that a moving clock runs slower than a clock at rest by a factor gamma. And this is true for both mechanical clocks and the light clock considered here. And actually, these results can be generalized by stating that all physical, chemical, and biological processes slow down relative to a stationary clock. When these processes occur in a moving frame, so observer O observes that the processes in this frame are slower than in his or her frame. Okay. So for the stationary observer O, the clock in O dash is running slow, right? While the observer O dash does not have any sensation of life slowing down in the vehicle, okay? For this observer O dash, it is the clock on Earth or O that is the one moving, and so it is the one keeping a slow time according to O dash. So this phenomena of time dilation is verifiable in, for example, experiments on muons reaching the Earth. So a muon is an unstable elementary particle that has a charge equal to that of the electron and a mass that is 207 times that of the electron, okay? And muons can be produced by the collisions of cosmic radiation with atoms high in the atmosphere. And they have an average lifetime of only 2.2 microseconds when measured in a reference frame at rest relative to the muons, okay? So if we assume the speed of the muon close to the speed of light, then they can travel a distance of only about 600 meters before they decay. And so they cannot reach the Earth from the upper atmosphere because they only travel 600 meters, right? But experiments show that a large number of muons do reach Earth, and the phenomena of time dilation can explain this effect. So relative to an observer on Earth, the muon's average lifetime is gamma tau, okay? And tau is equal to 2.2 microseconds, and it is the lifetime in a frame of reference traveling with the muons, okay? So if V is equal to 0.99 C, then gamma is equal to 7.1, and gamma tau is equal approximately to 16 microseconds, okay? And so the average distance traveled by the muons as measured by an observer on Earth is gamma VT, which is equal to 4,800 meters, as you can see here. And also in 1976, in the laboratory of the European Council for Nuclear Research, CERN, in Geneva, muons were injected into a large ring and reached speeds of approximately 0.9994 C, and the electrons produced by the decaying muons were detected using counters around the ring, okay? And this enabled scientists to measure the decay rate and therefore the muon lifetime, and it was measured to be approximately 30 times as long as that of a stationary muon, and this agreed with the predictions of relativity, okay? So the graph here shows the decay curves for muons traveling at this high speed and for muons at rest. So we will now discuss length contraction. So the distance measured between 2 points also depends on the frame of reference, okay? And the length of an object measured by someone who is at rest relative to the object is known as the proper length. And the length of an object measured by an observer in a frame of reference that is moving with respect to the object is always less than the proper length, and this is known as length contraction. So to understand this, suppose a spaceship is traveling with a speed v between two stars, and suppose there are two observers, one is at rest on Earth and the other is in the spaceship, okay? And the observer at rest on Earth is also assumed to be at rest with respect to the two stars. So suppose this observer here measures the distance between the stars to be Lp. And it is known as the proper length. So according to this observer on Earth, the time it takes the spaceship to move from one star to the other is delta t equal to Lp over v. And because of time dilation, an observer in the moving spaceship measures a smaller time of travel of delta t dash equal to delta t over gamma. And so according to this space traveler, he or she is at rest and the star of destination is moving toward the spaceship with a speed v and will reach this destination star in a time of delta t dash. And so this space traveler concludes that the distance L between the stars is shorter than Lp and is equal to L equal v delta t dash equal v delta t over gamma. And since Lp is equal to v delta t, L is equal, so it's equal to Lp over gamma. And so L is equal to Lp 1 minus v squared over c squared to the power half. And so as we said previously, because there is relative motion between this distance and this reference frame, unlike this frame on Earth, this observer will measure a contracted length, okay? And this factor here is less than 1, okay? And so if an object has a length of Lp when it is at rest, then when it moves with a speed v in a direction parallel to its length, it contracts to the length L, okay? And L is given by this equation. And note here that the length contraction takes place only along the direction of motion, okay? So let's consider another example of a stick that is moving past a stationary observer on Earth with a speed v. Then in that case, the length of the stick measured by an observer in a reference frame attached to the stick is the proper length Lp, because this observer in the frame that is attached to the stick is at rest relative to the stick, okay? And as we said, a frame at rest relative to the object or distance will measure the proper length. And the length of the stick measured by the observer on Earth is shorter than Lp by a factor of 1 minus v squared over c squared to the power half. So in this case, the relative motion is between the reference frame of the observer on Earth and the stick. So this observer on Earth is the one who measures the contracted length. Also, this length contraction effect is symmetrical. So if the stick is at rest on Earth, then an observer in a moving frame relative to Earth would also measure its length to be shorter by this factor, okay? And note here that proper length and proper time are measured in different reference frames. And as an example, let's go back to the muon decay example here, okay? So an observer in the muon's frame would measure the proper lifetime, while an observer on Earth would measure the proper distance traveled by the muons before they decay. And in the muon's frame of reference, there is no time dilation, but the distance of travel is shorter in its frame, okay? And for an observer on Earth, there is time dilation, but the distance of travel is the actual height and is the proper distance before the muons decay. So when calculations are made in both frames, the outcome of the experiment in one frame is the same as that in the other frame. So in summary, the length of an object measured by an observer in a reference frame that is moving with respect to the object is always less than the proper length Lp. And the one who is at rest relative to the object is the one who measures the proper length, okay? Also, for the distance between two objects, like in this example here, the observer who is at rest on Earth and relative to the two stars is the one who measures the proper length LP, while the one who is moving relative to the stars here in the spaceship measures a length contracted by a factor of 1 over gamma. Also, for the time interval, for example here, the observer in the spaceship who is at rest relative to the clock in the spaceship measures the proper time delta t dash, while an observer moving with respect to the clock in the spaceship, which is this observer here, measures the time interval delta t that is longer by a factor of gamma. So for this observer here in the spaceship, there is no time dilation, but length is contracted. And for this observer here, there is time dilation, but the length is the proper length, okay? And this is why the proper length and the proper time are measured in different reference frames. So as an example, let's consider a triangle spaceship passing an observer at rest on Earth, okay, with a speed of 0.9 c. So before the triangle moved, it was at rest relative to the observer on Earth, and it had a height of h and a length of LP, which is the proper length. Then while the spaceship is moving relative to the observer on Earth, he or she will see that the horizontal length of the spaceship is contracted to this length, okay? While the height of the triangle relative to this observer on Earth is unchanged because it is perpendicular to the direction of relative motion between the observer and the spaceship. So let's consider another example, which is the twin paradox. So consider an experiment that involves twins named Jack and Jill. And let's say at the start of the experiment they are 21 years old, and suppose the twins carry with them identical clocks that are synchronized. So this marks the start of the experiment. So Jill then sets out on a trip to planet X, which is at a distance of 10 light years away from Earth, and her spaceship is moving at a speed of 0.5 c relative to the inertial frame of her twin brother on Earth, okay? And after reaching planet X, Jill decides to immediately return to Earth at the same speed of 0.5 c. So upon her return, Jill was shocked to find that many things have changed, and her twin brother has aged 40 years and is now 61, okay? While Jill has aged only by 34.6 years. So the question is, which twin is moving and is younger as a result? So according to Jack's frame of reference, he was at rest while his sister traveled at a high speed, but from Jill's perspective, she was at rest while Jack and the Earth were moving away on a 17.3 years trip, then back for another 17.3 years. So this leads to a contradiction. And so which twin is younger after the trip? So to resolve this, note that special relativity involves only inertial frames moving at a uniform speed relative to each other. And Jill, the space traveler, does experience acceleration and deceleration during her trip, where she slows down, reverses her motion, and accelerates back to a uniform speed back to Earth, okay? So her speed is not always uniform, and so Jill is not in an inertial frame, so there is no paradox because it is incorrect to apply the special theory of relativity in this case. So only Jack, who is in an inertial frame, can apply the time dilation formula to Jill's trip. Assuming that Jill's time of acceleration and deceleration is very small compared to the rest of the time of her journey, so that Jill spends most of her time in the journey traveling in an inertial frame at a speed of 0.5 c. And so Jack does find that Jill ages by only 34.6 years, while Jill spends 17.3 years traveling to planet X and back for a total of 34.6 years. And direct evidence of time dilation was shown in an experiment conducted by Hafele and Keating in 1972, And in the experiment, the time intervals measured using 4 cesium beam atomic clocks in jet flight were compared to time intervals measured by atomic clocks in the Earth frame of reference. And the results agreed with the theory of special relativity, okay? And it was found that relative to the atomic time scale of the frame of reference on Earth, the flying clocks lost 59 plus or minus 10 nanoseconds during the eastward journey, and they gained 273 plus or minus 7 nanoseconds during the westward journey. So we will now discuss the Lorentz transformation equations. So in the video of special relativity part 1, we have seen that the Galilean transformation is not valid if the speed v is close to the speed of light. And here we will show that the Lorentz transformation equations apply for all speeds in the range of v greater or equal to 0 and less than c. So suppose an event occurs at a point P and is reported by two observers. So one is at rest in the frame S and the other is in the frame S dash, which is moving to the right with a speed v, okay? So the event for observer S occurs in the space-time coordinates x, y, z, t, while for observer S dash, the same event is described by these coordinates. So the Lorentz transformation equations provides the relationship between these two coordinates, okay? So they enable us to transform coordinates from the S frame to the S dash frame through the following equations. And it was developed by Hendrik Lorentz in 1890 in the framework of electromagnetism. But Einstein was the one to realize their significance later and incorporated them in the theory of relativity, okay? And as you can see from these equations, unlike the Galilean transformation where t is equal to t dash, the time t dash of the event as reported by the observer in S dash depends both on the time t and on the coordinate x, which are measured by the observer in S. And so in relativity, space and time are not separate concepts, but are interwoven with each other, okay? And to transform the coordinates in the S dash frame of reference to the coordinates in S, v is replaced by minus v, and the primed and unprimed coordinates are interchanged, and so we have these equations, okay? So if v is much less than c, then the Lorentz transformation will reduce to the Galilean transformation, because as v approaches 0, v over c square is much less than 1, and v square over c square is much less than 1, and so gamma is approximately 1, and the Lorentz equations will reduce to these equations, okay, which are the Galilean transformation equations. So in many cases, we want to know the difference in coordinates between two events or the time interval between two events measured by S and S dash. So the Lorentz transformation equations written to describe pairs of events is given by these equations. So these are to transform from S to S dash, and these are from S dash to S. So delta x dash is x2 dash minus x1 dash, and delta t dash is t2 dash minus t1 dash, are the difference in coordinates between two events and the time interval between the same two events as measured by S dash. And these here are the differences measured by S, okay? And note here that since the motion of S dash is along the x direction, the coordinates y and z are unaffected, okay? So we will now discuss the Lorentz velocity transformation, which is the relativistic transformation valid for all speeds from 0 to c, okay? So as before, suppose S is at rest and S dash is moving with a speed v relative to S, and suppose that an object is moving relative to the frame S dash, with an instantaneous speed ux dash equal to dx dash over dt dash, okay? And so if we substitute for dx dash and dt dash, and since ux is equal to dx over dt, we get ux dash is equal to ux minus v over 1 minus ux v over c square, okay? And in a similar way, if the object has velocity components in the y and z directions, then the velocity transformations are given by these equations, okay? Also, if ux and v are much smaller than c, then the denominator approaches unity here. And so ux dash is approximately equal to ux minus v, which is the Galilean velocity transformation, okay? And also, if ux is equal to c, then ux dash is also equal to c. And this shows that if the speed of an object is c relative to s, then it is also c relative to s dash. So it is independent of the frame of reference. And this is consistent with Einstein's second postulate, which states that the speed of light is c relative to all inertial frames of reference. Also, to find ux in terms of ux dash, we replace v by minus v and interchange ux and ux dash here, and we get this expression. So as an example, suppose that two spaceships A and B are moving in the opposite direction, and suppose an observer at rest on Earth in the frame S here measures a speed of 0.7 c for A and a speed of 0.8 c for B. Then we want to find the velocity of B relative to A, okay? So to solve this, let the frame S dash be attached to the spaceship A. Then the speed of S dash relative to S, which represents V, is equal to 0.7 c, right? And so the velocity of the spaceship B relative to the observer on Earth S is minus 0.8 c. So this is ux here, okay? And so the velocity of B with respect to A is ux dash and is found from this expression, and it is equal to minus 0.96 c. And so the negative sign here shows that the spaceship B is moving in the negative x direction as observed by the spaceship A, which is the S dash frame, okay? And note here that if the Galilean velocity transformation was used, then ux dash will be equal to ux minus v, which is minus 0.8 c minus 0.7 c equal to minus 1.5 c, which is greater than c, right? And this is why the Galilean transformation does not apply for relativistic speeds. So we will now discuss relativistic mass and the relativistic form of Newton's second law. And as we mentioned before, the laws of physics are the same in all inertial frames, and this requires the generalization of Newton's laws and the definitions of momentum and energy to conform to Lorentz transformations. And it was found that the classical definition of momentum, P equal mv, results in the momentum not being conserved in S dash that is moving at a high speed relative to S. For example, when describing a collision between two bodies in the frame S, momentum is conserved. Then if the velocities in the second frame S dash are calculated using Lorentz transformations and the classical definition of momentum, it was found that momentum is not conserved in S dash. But because the laws of physics should be the same in all inertial frames, momentum should be conserved in all systems. And so the definition of momentum is modified to satisfy the conditions of the momentum being conserved in all collisions, and that the momentum P approaches the classical expression mv as v approaches 0. And so momentum is conserved provided that m is equal to m naught over square root of 1 minus v square over c square, which is m equal gamma m naught, okay? And this is known as the relativistic mass, and m naught is known as the rest mass. And so the mass of a body moving at the speed v relative to an observer is larger than its mass when at rest relative to the observer, okay, by a factor of gamma. And this mass increase is reciprocal. So to an observer in S dash in the spacecraft, a ship on Earth will appear to have a greater mass. And so the measurements of mass, like those of space and time, depend on the relative speed between the observer and the thing he or she is observing. And in experiments, only atomic particles such as electrons, protons, and mesons have sufficiently high speeds for relativistic mass increase to be measurable, okay? And so when a force is applied to an object that is free to move, the force does work on the object that increases its kinetic energy. So the object will go faster and faster as a result, but because the speed of light is the speed limit, the object's speed cannot continue to increase as more work is done on it, right? And since the law of conservation of energy is still valid, then as the object's speed increases, so does its mass, so that as a result, the work done continues to become kinetic energy, even though v never exceeds the speed of light. And this graph here shows how at v equal to c, the mass goes to infinity. And so no material object can travel at the speed of light in free space, okay? And so the correct definition of momentum, valid for all speeds from 0 to c, is given by this expression. And so if p is much less than c, then the denominator approaches unity and p will be equal to m naught v, which is the classical expression for momentum, right? And we may write this as gamma m naught v. And the relativistic second law is given by F equal to dp over dt. And this expression here is not equivalent to Newton's classical second law, which is F equal to m dv over dt. And this is because d over dt of mv is equal to m dv over dt plus v dm over dt. And in this relativistic case, dm over dt does not vanish, okay? And so the generalized Newton's second law that is valid for all speeds from 0 to c is not F equal to m dv over dt, but it is that the resultant force on a body is always equal to the time rate of change of its momentum. So we will now discuss mass and energy. So the most famous relationship obtained from special relativity is the one concerning mass and energy. So we know that the work W done on an object by a constant force of magnitude F that acts through the distance S, where F is in the same direction as S, is given by W is equal to Fs. And if no other forces act on the object and the object starts from rest, then all of the work done on the object becomes kinetic energy, okay? And so W is equal to kinetic energy equal to Fs. And in the general case, when F is not constant, we can write it as the integration from 0 to S F ds. So in non-relativistic classical mechanics, the kinetic energy of an object of rest mass m naught and the speed v is equal to half m naught v square. So to find the relativistic formula for the kinetic energy, we start from the relativistic form of Newton's second law, okay? So which is F equal dp over dt, and we substitute, and then we use integration by parts to get this expression for the kinetic energy. And solving, we get this expression here, and this one is the relativistic mass. So we get the kinetic energy, the relativistic kinetic energy is equal to mc squared minus m naught c squared. And this shows that the kinetic energy of an object is equal to the increase in its mass due to the relative motion multiplied by the square of the speed of light, okay? And so the total energy of the object is given by mc square is equal to m naught c square plus the kinetic energy. And this shows that if the object is at rest and its kinetic energy is zero, it still possesses the energy m naught c square, which is known as the rest energy, okay, E naught of the object, which has a rest mass of m naught. So the total energy is equal to the rest energy plus the kinetic energy. And so if the object is moving, its total energy is given by m naught c square over square root of 1 minus v square over c square. And this shows that mass and energy are not independent entities. And the laws of conservation of energy and the laws of conservation of mass are one and the same, and is combined into the conservation of mass energy, okay? So mass can be created or destroyed, but when this happens, an equivalent amount of energy will simultaneously be created or destroyed, and vice versa. So mass and energy are different aspects of the same thing, and as you can see, the conversion factor between mass and energy is c square, okay? So 1 kilogram of mass has an energy content of 9 times 10 to the power 16 joules, which is really huge, right? So before Einstein's theory, no one was aware that this much energy was bottled up in such a small amount of matter. So what we perceive as solid matter is not solid at all, but it's made from energy. So solid matter can be converted to fluid energy and vice versa. And so relativity showed that the world is far more fluid than what was believed previously. So if the relative speed v of the moving object is small compared to c, then the relativistic kinetic energy will reduce to this familiar classical expression. So because v square over c square is much less than 1, we can use this binomial approximation, and if we substitute for x here, we get the classical expression of half m naught v square. And so classical mechanics represents an approximation that is valid for v much less than c. And the figure here shows how the kinetic energy of a moving object varies with its speed according to relativistic mechanics and to classical mechanics. So as you can see, at low speeds, the two formulas give the same results, but they diverge at high speeds. So we will now discuss massless particles. So in classical mechanics, a particle must have a rest mass in order to have energy at momentum. But in relativistic mechanics, a particle with no rest mass can exist, which exhibits particle-like properties such as energy at momentum. In relativistic mechanics, the total energy and the relativistic momentum are given by these expressions. So if the rest mass m naught is equal to 0 and v is less than c, then both E and P are equal to 0, right? And so a massless particle with a speed less than that of light can have neither energy or momentum. But if the massless particle has a speed equal to that of light, then both E and P are indeterminate. And so in this case, E and P can both have any values, okay? And so these equations here are consistent with the existence of massless particles that exhibit particle-like properties like energy at momentum, provided that they travel with the speed of light. So squaring E and squaring P and multiplying it by C square and subtracting this from E square, we get E square is equal to m naught square C to the power 4 plus P square C square. And so the total energy is equal to square root of E naught square plus P square C square, and this is valid for all particles. And for massless particles, E is equal to PC. And so this is another condition for a massless particle, okay? So relativistic mechanics does not exclude the possibility of massless particles, as we said, provided that the speed is equal to that of light and E is equal to pc. And two kinds of massless particles, the photon and the neutrino, have been discovered. So the usual unit of energy used in atomic physics is the electron volt. So one electron volt is the energy gained by an electron accelerated through a potential difference of 1 volt, okay? So since the work is equal to QV, we have 1 electron volt is equal to the charge of the electron 1.6 times 10 to the minus 19 coulomb times 1 volt, okay? So it's equal to 1.6 times 10 to the minus 19 joules. And higher energies in atomic physics are expressed in kilo electron volts. So in nuclear and elementary particle physics, the kilo electron volt is too small to be used, and the units used are the mega electron volt and the giga electron volt, okay? So this is 10 to the power 6 electron volt, and this is 10 to the power 9 electron volt. So for example, in nuclear fission, when the nucleus of a certain type of uranium atom splits into two parts, the energy released is about 200 mega electron volt. Also, the rest energies of elementary particles are usually expressed in mega electron volt and giga electron volt, okay? And the corresponding rest masses in mega electron volt over c square and giga electron volt over c square. So for example, the rest mass of the proton is 0.938 giga electron volt over c square. And suppose it has a kinetic energy of 3 giga electron volt, then its total energy is 3.938 giga electron volt, okay? And in a similar way, the mega electron volt over c and giga electron volt over c are sometimes used as units for linear momentum. The theory of special relativity was also able to find the connection between electricity and magnetism, okay? And one important point is that, like the speed of light, the electric charge is relativistically invariant. So if a charge has a magnitude of q in one frame of reference, it also has a magnitude of q in another frame. And so it was possible to show that all magnetic phenomena can be interpreted based on Coulomb's law, charge invariance, and special relativity. So consider two idealized conductors as shown here, and they contain equal numbers of positive and negative charges at rest that are equally spaced, okay? And so the two conductors here are electrically neutral and there is no force between them. So suppose now that these two conductors each carry a current, so I1 and I2 in the same direction. As you can see, the positive charges move to the right, the blue ones, and the negative charges, the red ones, to the left. And both have the same speed, v, okay? And this speed is relative to a laboratory frame of reference. And note here that in actual metals, the flow of charge is due to the flow of negative charges only, but this situation here represents an electrically equivalent model that is easier to analyze and will give the same results. So because the charges are moving, the spacing between them is now smaller by a factor of square root of 1 minus v square over c square. And because v is the same for both charges, the spacings contract by the same amounts, and so both conductors remain neutral relative to an observer in the laboratory frame of reference, okay? But still the conductors attract each other. So to understand why this happens, let's consider the conductor 2 from a frame of reference attached to one of the negative charges in conductor 1, okay? So the negative charges in 2 appear at rest in this frame of reference, and so relative to this frame of the negative charge in 1, the spacing between these negative charges is not contracted, okay? But the positive charges in 2 will now have a velocity of 2v relative to this frame of reference, and the spacings between them are contracted by a greater amount than in this case, which is in this case relative to the laboratory frame, okay? And so relative to this frame of reference here, conductor 2 appears to have a net positive charge, resulting in an attractive force acting on the negative charges in conductor 1. So now let's consider the situation relative to a frame of reference attached to one of the positive charges in conductor 1. So according to this frame, the positive charges are now at rest in conductor 2, and the negative charges are moving to the left with a speed of 2v, okay? And so the spacings between the negative charges is less than that between the positive charges, and so conductor 2 appears to be negatively charged relative to a frame of reference attached to this positive charge. And this results in an attractive force acting on the positive charges in 1, okay? And using identical arguments, you can also show that the negative and positive charges in 2 are also attracted to 1. And so all of the charges in each conductor will experience attractive forces towards the other conductor. And so this shows that although from the laboratory frame of reference, the mutual attraction between the wires is explained by a magnetic interaction between the currents, and although it is convenient to think of magnetic forces as being different from electric forces, they both arise from a single electromagnetic interaction between the charged particles. And the fact that a current-carrying conductor can be electrically neutral in one frame and not neutral in another is consistent with charge invariance, because one must consider the entire circuit of which the conductor is a part. So for a current to occur in a circuit, the circuit must be closed, and for every current element in one direction that appears to carry a positive charge relative to an observer, there must be another element in the opposite direction that the same observer will find negative, okay? So that the circuit as a whole appears to be electrically neutral to all observers. So in the following, I included some solved examples. So thank you for watching. Please don't forget to like and subscribe, and see you in the next video.